Hey everyone, welcome to Module 2.2. So in this module here, we're going to be going through applications and some problem solving, going through some specific problems, applying the key equations and concepts that we've learned up to this point. So objectives within this module, we will apply the concepts and equations from the previous module section to some example problems. So activities we're going to do is go through some applications, key equations, and problem solving. So in this first example problem here, we have a furnace for processing semiconductor materials. This is formed by a silicon carbide chamber that is zone heated on the top section and cooled on the lower section. So with an elevator in the lowest position, a rollbar arm is then going to insert a silicone wafer on its mounting pin. So we can see here, here's our elevator, here's our mounting pins over here, so there's our silicone wafer right there. So in production operation, the wafer is rapidly moved towards a hot zone to achieve the time temperature history required for the process recipe. So we can see here, here's our hot zone up top there. There's our cool zone down in the bottom there. So it's moved towards that hot zone. So in this position, the top and bottom surface of the wafer exchange radiation with the hot zone and the cool zones respectively. So if we take a look over here, you can see there's your wafer. There's the top surface, bottom surface. We can see that the top surface is in the hot zone and the bottom surface is in the cool zone. Now it also tells us that the zone temperatures, TH is equal to 1500 units of Kelvin, and TC is equal to 300 K right there. So there's your TH equal to 1500 Kelvin, and TC is equal to 300 Kelvin. Again, pay attention to our units as we're doing this. Now they also give us our emissivity and thickness of the wafer. So these are, our epsilon value is 0.65 and our thickness D is 0.78 millimeters. So again, pay attention if we're in millimeters, meters, make sure we do our conversions correctly later on. They also tell us we have an ambient gas at a temperature of T infinity is equal to 700. So there's our T infinity of the gas right there. They also give us our convection coefficients at the upper and lower surfaces of the wafer. So we can see our convection coefficients there and there. And these are 8 and 4 in units of watts per meter squared times Kelvin. So again, pay attention to your units as you're doing these. Now for the silicone wafer itself, it tells us it has a density given to us as 2,700 kilograms per meters cubed, and a specific heat given to us as 875 units of joules per kilogram times Kelvin. Now, within this problem here, they're also asking us to solve for a couple different things, A and B. So for part A, they tell us for an initial condition corresponding to a wafer temperature. So they give us that initial wafer temperature, T temperature, W wafer, I initial, is equal to 300 K. And they also tell us the position of the wafer is shown in the schematic above. They want us to determine the corresponding time rate of change. It's a time rate of change of the wafer temperature, which is d dt of TW right there, initial. Now in part B, what they want us to find is the steady state temperature reached by the wafer if it remains in this position. They also ask us how significant is the convection heat transfer for this situation, and to do a sketch. We won't be doing the sketch for this solution here. We'll just be doing the first part A and then finding in part B the steady state temperature. So now I'm going to zoom in a little bit closer on our given schematic diagram here and review this problem here. So in 1.57, we have a thermal processing of silicone wafers in a two-zone furnace. So we can see our two-zone furnace here. We've got our hot zone and our cold zone with the associated temperatures there. They want us to solve for two different things here in part A, the initial rate of change for the wafer temperature, and in part B, the steady state temperature. So that's what we're going to be solving for here. We can go through and we can see all the individual components right here. We have that gas, our ambient temperature, T sub infinity there, our wafer with its associated temperature. We have our H for lower, H for upper in the hot and cold zone respectively, and we have our mounting pin and our elevator right here. So what is known? We know that silicone wafer is positioned in the furnace with the top and bottom surfaces exposed to that hot and cold zones right there. So there's the wafer, hot zone, cold zone there. And again, what are they asking us to solve for? Two different parts, A and B. In part A, they want us to find the rate of change, the initial rate of change of that wafer's temperature. So they give us the initial value here of TWI, the temperature of the wafer, initially is 300 K. And in part B, we're finding the steady state temperature. So the next thing that we need to do with any of these problems is take that big figure that they give us in the problem statement and draw out a close-up schematic diagram that we can use with all of our information associated with it. So this is just an example of that there that's drawn out, and you can see how much information is there. Now, one of the things that I want to note with this is the fact that maybe we don't include every single value. Maybe we just include the variable names right there, and then on a separate setup sheet, that's where we can say, okay, our T infinity is equal to 700K. Our HU is 8 watts per meter squared times Kelvin. So all of that information, I think, would be better to take off this so it's not quite as jumbled as we're seeing here. And all this information over here associated with our wafer, well, we can put that separately as well on our setup page. This doesn't need to necessarily go into this diagram right here. Just the individual variable names that are important. So that's what I do here. The first step in coming up with solving this problem is to create my setup page. So with this setup page right here, I have the problem number up top here, problem number 1.57, and then all of that given information. So reading through that very wordy problem statement and taking a look at that pretty involved initial given figure, I can take all this information here. And I want a couple different things, 3 or 4 different things for each of these. I want the variable name, I want the value, I want the units, and then maybe even a note of how it relates to this physical problem. So I have my T sub H, temperature in the hot zone is 1500 K. I can come over here and I can see there's my T sub H right there in my simplified version of this diagram here. So I have my wafer right here. I have my temperature of the cold zone right here, 330 K. There's my cold zone right there, T sub C. I have my T sub infinity of the gas right there, and this is equal to 700 in units Kelvin. I have my convection coefficient right here, my H upper. So my H upper here is 8 watts per meter squared times Kelvin, and I have my H lower, convection coefficient of the lower is 4 watts per meter squared times Kelvin. I have the wafer thickness here, which I can see right there, is D, and this is equal to 0.78. Be careful now, we're in millimeters and everything else we've done is meters, so make sure you do the conversions correctly. Oftentimes, it's not a bad idea to even do it right here and write it out what it would be in meters there so we can plug in correctly later. I have my density, my rho here of 2,700 kilograms per meters cubed. And I have my C, my specific heat value of 875 joules per kilogram times Kelvin. And I have my emissivity here, epsilon is equal to 0.65, no units. And I have my initial wafer temperature, T, W, comma, I is equal to 300 K. So this is great to have this setup page ready to go so we can quickly reference back, see an overview of the schematic of what's going on in the problem, and have all of my variable names, values, and units ready to plug into whatever governing equations we use. So the next thing that we want to do as we begin our solution is come up with any assumptions. So what are assumptions that are going to be made with this problem here? Well, one, we're going to assume that the wafer temperature is uniform. 2, the hot and cold zones have a uniform temperature. We're also going to assume that radiation exchange occurs between small surfaces in a large enclosure. And our last assumption we're going to make is there's negligible heat loss between the wafer and the pin holders. So for all of these, it does simplify down our solution to the problem slightly. Then I clearly want to have labeled on my setup page what I am solving for. This becomes very important, especially with more involved problems, of understanding what I've solved for so far, but what did they really ask me to solve for? So 2 different things. The first thing they want to solve for is the initial rate of change of the wafer temperature from our initial value of 300 K. And part B, we need to find our steady state temperature. Now, continuing on, they could ask us to do more. Is this convection significant? And to sketch some stuff out. We're not going to include that for our solution here. So the first thing we want to do as we get our solution to these problems is to figure out what our governing equation is. And oftentimes the best way to figure out what governing equation we're going to utilize is to go back to that setup page, look through all the given information and what they've also asked us to solve for. With that information, we can then come up with a governing equation. Now, when I'm choosing governing equations, I really like to pick a very, very general one and expand upon it from there. So what I've done here is I'm going to go back to the first law of thermodynamics here. And a refresher, the first law of thermodynamics, what this states is the increase in the amount of energy stored in a control volume must equal the amount of energy that enters the control volume minus the amount of energy that leaves the control volume. So you have your inflow and your outflow here. So we have this governing equation from the first law of thermodynamics. We have our delta EST total, which is the change in the total energy. So delta is change, E is total energy right there with the total on the top, stored in the system. There's our ST right there. So this kind of just relates to how we're going to use indices and variables to actually say what the things are that we're plugging in for in our governing equations. Q in our equation here is the net heat transferred to the system, and W is the net work done by the system there. So this comprises our first law of thermodynamics for our governing equation. So as we continue on with our solution here, we want to take a look at energy balance on the wafer, including the upper U and lower L surfaces from the ambient gas, radiation exchange with the hot and cold zones. Remember, it's a two-zone furnace, it has the hot and the cold zone, and energy storage term for the transient conditions. So now we can take and rewrite this as equation 1.12 in our textbook here, where we have our E dot ST, which is our stored thermal and mechanical energy. This is equal to our E dot N, which is the inflow, which is thermal and mechanical energy transport across the control surface, minus our outflow over here, our E dot out, which is thermal and mechanical energy transport across the control surface there. So for thermal energy with time, change in thermal energy with time, we want to recall the following relationship down here. So E dot ST is equal to du dt, which is equal to d over dt, change with respect to time, of rho v ct, where rho is going to be that mass density, c is our specific heat, and v is the volume of the plate. So for our specific problem, this is just 1D. So for a 1D problem, the v, the volume right here of the plate, is simply the thickness d. So we can sub that out for our v, put in our d there, pull out our constants, so we end up with this relationship here that our E dot ST, or our stored thermal and mechanical energy, is equal to rho CD times d over dt of T, or change in temperature with respect to time. So now we can look at this per unit surface area. And what I want to do is take a look at each individual component. So like I said, I'd like to have that real general equation that we can then plug in the specifics for here. So I have my E in minus my E dot out is equal to my E dot ST over here, where E in is the inflow, which corresponds to the mechanical work. E dot out is our outflow, and E dot ST is our stored thermal and mechanical energy there. So we've already found this equation here on the previous slide for the relationship for our stored thermal and mechanical energy. So now we need to find terms where we plug in for our inflow and our outflow here. So this is where we can say, well, our inflow is going to be the radiation coming in from the hot zone and from the cold zone, and our outflow is going to be right here, our heat flux for the upper and lower right there from convection. So we have convection there, radiation here. So for our radiation and our inflow term right here, we have our radiation is equal to, in this case here, we have our epsilon sigma, and this is times the temperature difference between our T sub S and our T sub surround there to the fourth power there. And this is a general radiation equation for our heat flux right there. And now for our convection term right here, we have that this is equal to our H value, or our convection heat transfer coefficient, times our temperature difference between T sub S and T sub infinity, our surface temperature and our gas temperature in the surroundings there. And this is our general convection equation for heat flux there that we can go back into our book and review. So basically we're plugging in our general radiation equation and our general convection equation into this energy balance equation up here for our inflow and our outflow. And we've already found our stored energy term here on the previous slide there, given by this relationship relating to our density, specific heat, thickness, or volume if we're looking at more than a 1D problem there. And then this right here is our change with respect to time of our temperature of the wafer. So this now gives us a general equation that we've expanded upon here. We can plug in for this specific problem here, and we have our radiation term, our convection term, and that stored energy term over here. I still like to look at these separately. Even though I've wrote it out as one long equation here, I still want to deal with each one of these separately. Let's just deal with the radiation term, just deal with the convection term, just deal with the stored energy term here, because there's a lot going on in here. When you have this much going on, this many variables here, you don't just want to throw all the values in there, all the numeric values we have. It can get very confusing. We could lose a negative sign, we could drop a decimal somewhere, get something off a little bit. So I'd like to deal with these individually and separately to keep it neat and organized and reduce any possibility of errors when we're plugging in. So now what I have here is I've rewritten my governing equation right here with individual sections. I'm going to deal with radiation, then I'll deal with convection, and then I'll deal with the stored energy term. break it down separately, keep our lives easy. Then the next part we do is if we're dealing with a radiation term here, let's plug in our numeric values. Now we can go back to that setup page that we created. Those are all neatly labeled and organized, our variable names, numeric values, and our units. We can plug straight in. Speaking of units, we want to pay attention to those and write those out so we can do unit analysis to make sure that everything is correct as we do that. So now we'll deal with just the radiation portion of this here. We see our epsilon value. We go back to our setup page. That's equal to 0.65. Now we have our sigma here, our Stefan-Boltzmann's constant. This is 5.67 times 10 to the negative eighths units of watts per meter squared times Kelvin to the fourth. This is now times our temperature difference here. And as we plug in our values, 1500 to the fourth, 300 to the fourth there. Units are K to the fourth. Now we can notice here, this K to the fourth right here and the K to the fourth right there cancel out, leaving us with watts per meter squared. Now we can move on to the right-hand side of our radiation portion of this equation here. Our epsilon is 0.65. Our sigma is 5.67 times 10 to the negative eighth again in units of watts per meter squared times Kelvin to the fourth right there. And this is multiplied by our temperature difference to the fourth of 330 K to the fourth minus 300 K to the fourth, which would give us a K to the fourth and a K to the fourth that cancel out. So we're left with watts per meter squared. Watts per meter squared added together is units of watts per meter squared. So therefore our EN, our inflow right here, for our radiation term right here is going to be equal, when we solve this out and plug it in, 186,418.5, 186,418.5 in units of watts per meters squared. So that's great. Those are the correct units that we should have. That checks out. Now we can move on to our second portion of our equation here, our convection term. So looking at our convection, we can plug in our H values here, our upper and lower. So we plug that in, -8 units of watts per meter squared times Kelvin times temperature difference of 300 minus 700 when we plug in for those values for TW and T infinity right there. Units of Kelvin, we can see Kelvin cancels with Kelvin there. Now minus the right-hand side, our H value here is 4 times, now we can see in units of watts per meter squared times Kelvin times the temperature differences, again, TWT infinity of 300 and 700. Kelvin cancels with Kelvin there, left with watts per meter squared. So our outflow when we plug this in is 3,600 or 3,600 watts per meter squared. Units check out for both of these. We're looking great so far. We've dealt with the radiation and the convection, or the inflow and the outflow terms. Now we can deal with the stored energy term on the right-hand side of this here. We plug in for our rho from, again, our first setup page there, 2,700 units of kilograms per meter cubed. Now we have our specific heat of 875 joules per kilogram times Kelvin right there. And this is times 0.0078 right here that we've already solved for. We'll plug this in. This is units of meters right here. Now this is, when I say solve for this, what we've done is we converted from millimeters to meters of the wafer thickness that was given in the problem there. So that is something that is important. Don't put that in terms of millimeters, put it in meters. And if you were doing your intercept analysis correctly, that should have popped out right there and saw that that wasn't the same. So we can see that that meters cancels with this guy down here to reduce that down a little bit with that exponent there. And this is now times our dt of our temperature of the wafer right there in units of Kelvin per second there. So we can see our Kelvin's going to cancel with our Kelvin over here. So we're left with is our E dot ST right there is now equal to, if we can take a look at this here, units now, joules per meter squared times seconds. So we ask ourselves, can we do that conversion? Joules per second is watts, so watts per meter squared, watts per meter squared. This does double check, and it matches with everything else up here of watts per meter squared. We really want to do that unit analysis out as we're solving this problem. So now we want to plug in our values here, and what we do, we deal with the left-hand side, solve those. You can plug this into a calculator, MATLAB, Excel, even by hand. This one's simple enough. You end up with this term right here. You have 186,418.5 plus our 3,600 for our inflow and outflow, and this is equal to, when we do our math here for the beginning part of our stored energy term here, we end up with 1,842.75 times what we're looking to solve for in this problem, which is the change with respect to time and the temperature of the wafer right there. We can rearrange, add these two guys together, divide by this here to get this on its own, and we do that, we can plug and chug. We end up with our change, our time rate of change of the wafer temperature right here, ddt of our TW right there, is approximately equal to 104 kelvins per second. Does that make sense for units? Well, it's the time rate of change of wafer temperature, so there's our time and temperature right there. Yes, that does make sense for our units. So that was solving for part A in our problem. So now what we want to do is move on to part B, our steady state condition here. So when we're dealing with steady state, what this means is that our energy storage term is then 0. So on our right-hand side of the equation right here, our EST, our storage energy term, is equal to 0. So therefore we can plug that in. It simplifies down that general governing equation. So our energy of balance equation can now be solved with a steady state temperature when we're saying that T sub W is equal to T sub W steady state right there. Temperature of the wafer is equal to temperature of the wafer steady state. So this term goes right away to 0 right there. We're just left with now our inflow minus our outflow is equal to 0 there. So we have already solved for our governing equations to plug in our relationships for our inflow and our outflow right here. So we can say our inflow was dealing with radiation, our outflow was dealing with convection term right there. So we had those terms that we plugged in. We had for a radiation term. Now we have all of this right here for radiation. This is convection right there. So in our radiation term, we have our emissivity right here times our Stefan-Boltzmann's constant times our temperature difference between TS, and now this is our temperature of our wafer steady state right there. Plus, again, the right-hand side of this first term for our inflow here is our epsilon emissivity times Stefan-Boltzmann constant right there times our temperature difference between, again, that surface temperature TS and our temperature of our steady state temperature of our wafer right there. We do this out right here. And what we can see, just pay attention, these are temperatures to the fourth right there, so it's Kelvin to the fourth with those for the temperature differential portion of this here. Now this is going to be minus our H values times our temperature differences there for the hot and the cold zone, or upper and lower zone right there. And we can see, again, this is the temperature of the wafer steady state when we plug into both of those there. So now we can move on with that governing equation, plug in our known numeric values here. So we plug those values in. There's our epsilon for emissivity right there, 0.6. So that's a 0 right there, 0.675 times our Stefan-Boltzmann constant right there times our 1500 times, now the difference is what we're looking for, that steady state temperature of our wafer right there. Again, pay attention, those are Kelvin to the fourth minus the right-hand side of that term for radiation right there. Our inflow, 0.65 for emissivity right there, our epsilon value there. Stefan-Boltzmann constant, we can plug in that numeric value there times our temperature difference right here. Again, now this is what we're solving for, our TW, our temperature of our wafer at steady state, is equal to, this is our inflow portion. Now we'll do our outflow portion right here, which is our convection term right here, plug in our H values in watts per meter squared times Kelvin. This is times our temperature difference. And again, this is what we're searching for right here, so we want to solve for is temperature of the wafer steady state. Units of Kelvin right here, not to the fourth in this one here. Do the same thing over here. Again, upper and lower, hot and cold zones. Pay attention to our units, do our unit analysis with this here. Our kelvins cancel with our kelvins there. We're left with watts per meter squared, as we should for our outflow there. And that's our E out right there, outflow right there. So now our only unknown within this relationship is our T sub WSS, or the temperature of our wafer at steady state, which is exactly what we're looking to solve for. You could do this by hand. It's simple enough. You can put it into a calculator, MATLAB, Python, Excel, whatever your choice is. We do that. We end up with our temperature, steady state temperature of our wafer of 1,251 Kelvin. And that was part B that they asked us to solve for. So now we've gone through, we can go back to our setup page, say, okay, they asked us to solve for this in part A, done. They asked us to solve for steady state temperature in part B, done. I have completed everything they've asked me to solve for.